Okay, so before we can understand the concepts of effusion and diffusion, right, or diffusion and effusion, the way that it's titled, we have to understand something called the mean free path. And really, that's just how far something can travel before it strikes something else. So, give you an idea, just like at a people level, before I go into the details of this slide, which are all stolen out of the book, by the way. But if you were in Reedley, right, and you're walking around the street on a Sunday afternoon, your mean free path would be quite large because there's hardly anybody out on a Sunday afternoon. Most people are in their houses these days right now, or they're out doing something else. But the population density is really small. On the other hand, if you were to do the same thing in New York City, you would be running into people all the time because there are just so many people in New York City. And so the mean free path is essentially how far you could travel before you run into somebody else. So to put that in perspective for molecules, oh, and this is pretty much a reasonably good depiction of what a molecule does in the course of its life in this container, right? It just goes around and careens off different things, and then periodically it runs into another molecule, like perhaps right here, for example. All right, so let me go ahead and read this description to you or with you, right? It says at room temperature and atmospheric pressure, because the pressure is like the population density. If the pressure is high, the population density is high, right? And there's a lot of collisions. So we got to think about, we got to set that criteria. So at atmospheric pressure, the mean free path of a nitrogen molecule with a diameter of 300 picometers. Now, 300 picometers is, and I'm just doing this because what's coming up, is about 0.3 nanometers. Just to put it in perspective, this is 0.300 nanometers. So that's about how big a molecule is, okay? And it travels 93 nanometers before it hits anything. So if you take 93 nanometers, right? Oops, that's millimeters, sorry, nanometers, and you divide it by 0.3 nanometers, that's where you get this number of about 310, right, molecular diameters before you run into something else. So this ratio actually comes out to 310. That's where they get their numbers. Anyways, now if you put it into perspective, right, if it was a golf ball, it would go about 40 feet. That would be 300 times the diameter of a golf ball. It would go about 40 feet before it ran into anything else. Now, the thing that makes this happen all the time, though, because it sounds like, well, then it never happens, right? But the thing that makes this happen all the time is that gas molecules are moving so stinking fast that they're always running into stuff. Going the 300 diameters takes it no time at all to get across that distance, and then it finds something and runs into it. So think about this happening, right? And you have something that looks like this, right? Now I drew the molecules a little big, like relative to their diameter, but you could just think of this as being at high pressure. And now we're ready to talk a little bit about the process of diffusion. And let's say, again, you have to think about these are not static. These are gas molecules in a container. And then you have this one particle, and he wants to get over here, okay? So what happens, right? So let me go ahead and get a pen going here. Well, he might travel like over here and then hit something and go like this and here and here and here, here and here. Now, gradually over time, his path will get wider and wider. He can't just go like the ideal and end up over on this side. Okay, so this is the process of diffusion. It's kind of what we call a random walk. In fact, there used to be a name to this. It used to be called the drunken sailor. This was years ago, and it was like a drunken sailor trying to find his way home, and he just did it by process of diffusion. He basically walked around and ran into things enough until eventually he got home. Right? That's what these gas molecules are all doing. And so over time, the radius in which it travels increasingly gets bigger and bigger and bigger, it actually turns out to take essentially exponentially longer to travel further away. So, how do we experience this phenomenon in every day, right? When you when you when you're in a room, let's say a classroom, right, and somebody comes in with cologne on, you don't smell that person immediately. What has to happen is the gas molecules have to travel by process of diffusion, and in a room there's also convection, so that speeds it up a little bit, like just air currents moving around. But that air, those scent molecules have to get to you by process of diffusion. So even though they're going hundreds and hundreds of meters per second, right, easily enough to cover the span of the room, they have to go by this slow process of diffusion to spread out into the room. And essentially that pattern is circular. That is, from the point of origin, like I'm showing here, these molecules slowly and randomly begin to spread around, so that one little red molecule, which is hiding down in here now, the little oblong one that I put in there, right, in order for it to travel all the way here, it does actually take a certain amount of time for that to happen. So this is the process of diffusion, right? It's a process in which molecules in an atmosphere randomly, or even without an atmosphere, randomly spread out in a container and eventually fill the container. So a related process is known as effusion, and you could think of it as molecules in a container sort of randomly traveling around over on this side. And this container, this half of the container, contains all the molecules initially, but it has a hole in it. It actually has a leak. And we don't have any other gas molecules in here. So usually this is done in a vacuum, where you put a gas sample in one side and then there's nothing on this side, right? So effusion is the passage of gas molecules from a container, leaking basically. And it turns out that if you have two different molecules, you can calculate the relative rates of effusion based on this equation here. Now, what does this equation come from? If you have, if you remember the RMS velocity equation, mu is equal to, right, 3RT over the molar mass. So this is, say, of A, so I'm going to put an A down here. Now this is a square root like that. You notice the velocity is inversely proportional to molar mass. Well, the rate at which a molecule will come through that hole is actually dependent on how fast the molecule is traveling. The faster it travels, the more collisions it makes, the quicker it'll find the hole in the wall and leak out. So we can see then, just based on this idea, that rate, right, is going to be proportional to 1 over the molar square root of the molar mass. So rate of A is proportional to 1 over the molar mass of A. That you can come up with this equation, provided that the proportionality constant between those two variables, rate and molar mass, is the same. And it turns out when they do this experiments, they set them up so they would be the same. So how would we use this information in a problem? So here's one example of a calculation that you can do. It says a sample of N2O effuses from a container in 42 seconds. How long will it take the same amount of gaseous iodine to effuse from the same container under identical conditions? So basically what we need to do is know what the relative rates are, and we want to know the rate of N2 relative to the rate of I2. So that's going to be using Graham's law of effusion, which is what that equation was that I showed you. Right? It's going to be related to the inverse of their molar masses. So I would put the molar mass of I2, which is 253.809 grams per mole. And then for the, N2O, for the molar mass of N2O, it would be 44.013. Okay. And I can calculate that as 2.315, right? And it doesn't have units because the units all canceled out. But what this means is N2O effuses 2.315 times faster than I2. So if it takes N2O 42 seconds, right, it's going to take I2 42 seconds times 2.315 times, because that's how many times faster N2O travels or effuses relative to I2. Oh, I put another times there. That's going to be equal to 97.2 seconds. And you can always check your results. They'll make sense in terms of if you get it right, the heavier gas should be traveling, should take longer because its effusion rate is lower because it has the higher molar mass. Okay.